Hey guys, happy end of summer. Now that most of you have completed the first summer assignment, I wanted to take an opportunity to go over a few of the problems that gave everybody a little bit of difficulty. They were kind of challenging, and it's summer, and you have been tasked largely with learning or reviewing a lot of this stuff on your own. Some of it's new, some of it's challenging you to think a little bit deeper and or maybe pay attention to some subtle details that maybe weren't as important last year in honors chem. So I just want to, there's 4 or 5 problems here. Hopefully this video won't last too long. Feel free to skip ahead to the next problem if you understood the one that I'm currently reviewing. So this problem, I think, gave everybody a bit of a challenge, and it came in one of 2 forms. It came in a form like this, where you're comparing C3H8 and C4H8, or some other variation on this. And in each case in this problem, right, the ratio here of carbon to hydrogen is different. Right, in the case of C4H8, it's 1 carbon for every 2 hydrogen, but that's not the case in C3H8. So since those ratios are different, they have different empirical formulas. And in fact, the empirical formula here is CH2O, or sorry, excuse me, not CH2O, but CH2. And here the empirical formula is C3H8. Right? You can't simplify that down anymore. And so they will have a very different percent composition. And since they have a different percent composition, then they will have different empirical formulas. So you will be able to tell the difference between the 2 of those since they don't have the same empirical formula. In contrast, where we have C5H10 and C7H14, both of these have the same empirical formula. Right? If I simplify those ratios down, it comes to a 1:2 carbon to hydrogen ratio. And so they have the same percent composition by mass if you go ahead and calculate those out, which then means you couldn't tell the difference. Right? The percent composition of CH2 is the same as the percent composition of C5H10, is the same as the percent composition of C7H14, and would be the same as the percent composition of C8, H16. As long as it's at 1:2 ratio, you will not be able to tell the difference between the 2 in some kind of analysis. So moving on to the next problem, the electrolysis of water. Water decomposes into the component elements hydrogen and oxygen. So if we write a balanced equation for this, H2O becomes H2 and O2. And then, of course, we need to balance that. So we're going to have a 2 there and a 2 in front of the H2, and that should balance that equation. It says when it's decomposed, when electrical current is passed through it, the volume of hydrogen collected in the right test tube is twice the volume of oxygen. And if you look at those numbers and compare them to the coefficients in the equation, it's interesting that they're the same, or maybe it's not interesting that they're the same. But what you hopefully get from that is that if the volume of H is 2 times the volume of O, and that jives with the coefficients. If you remember back to talking about stoichiometry, right, the coefficients are a mole ratio. And so it's a 2-to-1 mole ratio as well. And so if that's the case, the relative gas volumes collected in 2 tubes relative to the number of gas molecules in the tubes, well, the ratios are the same, right? If mole ratio is the same as the volume ratio, well, then the particle ratio will be the same as the mole ratio, which will be the same as the volume ratio. Now, maybe the wording in this question is what threw you. Maybe not. Only you know the answer to that, right? They are the same. All right, the next one was dealing with you creating your own kind of temperature scale. Well, if we're going to create this new temperature scale, and it's called degrees A. I think in the problem it was called degrees O, but when I write an O and a 0, it's hard to tell the difference between the two, so I changed the O to an A. And so if on the normal scale, oleic acid has a freezing point of 13 degrees Celsius and a boiling point of 360 degrees Celsius, right? What would it be? Well, we're asked then what would be the freezing point of water if on the A scale we have a freezing point of 0 degrees A and 110 degrees A. Well, we need to find the relationship between degrees Celsius and degrees A. And so the degrees Celsius here, that is a 347 degree change. And here, that is a 110 degree change. So we have a conversion factor that says 347 degrees Celsius for every 110 degree A. And so now we have to find the freezing point of water in degrees A. So how do we go about doing that? Well, we know the freezing point of water normally is 0, right? So let me write all that in up here. So for water, the freezing point is 0 degrees Celsius, and the boiling point is 100 degrees Celsius. I don't need the boiling point, I just need the freezing point. So if the freezing point of water is below the freezing point of oleic acid by 13 degrees, then on the new scale, it's going to be, the freezing point of water is going to be still lower than the freezing point of oleic acid on the degrees A scale. The question is, by how much? Well, the difference here in the Celsius scale is 13 degrees. So if we have 13 degrees Celsius, what is that difference on the oleic scale? Well, I know that there's 110 degrees A for every 347 degrees C. That gives a temperature of about 4.1 degrees A. Now, since I know that the freezing point of water is going to be less than the freezing point of oleic acid on this new scale, then the freezing point of water is got to be equal to negative 4.1 degrees A, right? It's gone down by that much. And then the last problem, and this is the one that if I got emails, this is the one you emailed me about. And I really think this one's going to come down to careful reading of the problem. So the problem reads, there are two different isotopes of bromine atoms. Under normal conditions, elemental bromine is bromine molecules. And the mass of the bromine molecule is the sum of the masses of the two isotopes in the molecule. This mass spectrum down here is of Br2. It's of the molecules. It's not of the atoms. We are also told in this problem that there are two isotopes of bromine atoms. So I'm going to call them atom A and atom B. Well, if Br2 is two atoms of bromine, well, how many different combinations can I get from two isotopes? Well, I could have A and A. I could have B and B, or I could have A and, well, it's not A and D, A and B. And each of those would have a unique mass. And that is where the three different peaks are coming from in the mass spectrum of BR2. Hope that was helpful. Hope this video didn't go on too long. Hopefully you watched it. And my biggest thing in AP Chem is that if you don't understand something, you ask the question and then figure out where your mistake was. Right? If you're going to learn from your mistakes, hopefully all year, you're going to make plenty of them. Right? This is AP Chem. This is a college course. You're not yet in college. And if you already knew how to do this stuff, you wouldn't need to take the course. So you're going to come up against things that you just don't know how to do or that you haven't thought through yet. And then you'll ask questions and I'll help you through it. And then I want you to go back and find the error in your thinking so that when you approach another problem, you're better equipped to handle that one. All right, guys, looking forward to seeing you in just a couple of weeks. Take care.